Hello, in this video we're going to be looking at section 9.4 derivative formulas. The goal in this section is to develop some shortcut rules so that we don't have to continue using the limit definition of a derivative. So let's begin by looking at the limit definition of a derivative one last time. We know that a derivative is defined to be the limit of the difference quotient as h approaches 0. So we'll do this for the function x cubed, and then we won't give like a formal proof, but we'll talk about a pattern that we can notice from this, and then we'll end up developing what ends up being called the power rule. So to take a definition using the limit, we begin by just examining this difference quotient, and this would be equal to x plus h cubed minus x cubed all over h. And when we simplify this, we want to expand x plus h cubed out. Now this does take a little bit of work. What you have to do, I'll do it up here off to the side, is you have to take x plus h and multiply it to itself 3 times. Which is going to require a fair amount of foiling. I'll pause the video and show you what I get. Alright, so all of that just shows us that this first part becomes x cubed plus 3x squared h plus 3xh squared plus h cubed. We're still subtracting h cubed, or x cubed, and then dividing by h. So looking at this, we have a little bit that will simplify for us. If you subtract a positive x cubed, if you subtract x cubed from positive x cubed, then that'll just reduce to be 0. Everything that's left has an h in it, so this will be equal to, I'm going to factor that h out of my numerator. We'll be left with 3x squared plus 3xh plus h squared. Then in my denominator I have h. We see that these reduce. And then at the very end of the problem, well, it's kind of the main point of the problem, but we also do it at the end. We consider the limit of that as h approaches 0. So it's the limit of 3x squared plus 3xh plus h squared. And if h is approaching 0, we just try direct substitution. You put 0 in for h, and we find that we got 3x squared as our answer. So this is f prime of x if our original function was just x cubed. When you compare these two, you should notice, like, wow, that was a lot of work, but there seems to be a pattern between my answer and the initial question. In fact, the exponent started out as a 3, and I see a 3 now showing up as a coefficient, and then my new exponent is 1 less than what it used to be. And you might wonder if that pattern holds. So I'm not going to go through like the process of actually finding it, but if I take these next 3 derivatives, what you're going to find is that the derivative of x squared is 2x, the derivative of x to the 4th is 4x cubed, the derivative of x to the 5th is 5x to the 4th. And the pattern you notice, the exponent kind of migrated out in front to become a coefficient. That happens every time. So we see those showing up there. And then the new exponent that we have is always 1 less than the previous one. So this right now is not a proof of the rule. It's just an indication that a rule might exist. There is a proof in the textbook if you're curious about why this has to be true for all possible exponents, for all real valued exponents. But the official power rule is this, kind of what we indicated. If you have this function here, just x raised up to the n, then its derivative can be computed by doing what we were describing earlier. You take the exponent, it migrates out front as the new coefficient, then the new exponent is 1 less than what it previously was. So let's go ahead and do just some examples of this. Now I'm going to use some notation that we haven't heretofore used very much in this class, but one way to ask about a derivative is I could ask you, what is d dx of something? So I'm going to pick on something that I've already written down at the top of the screen, just to emphasize what the notation means. This means take a derivative of this function, or what is the derivative with respect to x of x to the fifth, and then based on what we've written up above, we would say, oh, well, that's just 5x to the 4, and that's it. So that's our answer. Some other derivatives that we can now compute with this, d dx of x to the 200 is equal to, well, we just apply that same rule. The 200 migrates out in front. Then we reduce the size by 1. So I have been saying reduce the size by 1, which is maybe a little bit of a misnomer as we get into future examples. What we are technically doing is we are subtracting 1 from the exponent. So the new exponent will be 199, and then we have this as our answer. The reason it's a little bit of a misnomer is we're going to run into problems where you're going to have to do a little bit of an algebraic manipulation in order to apply this rule. For instance, what is the derivative of 1 over x to the 10? Well, in order to think about this, you first of all want to rewrite it as x raised up to some exponent. Now, there are algebra rules that tell me that if we give it an exponent of negative 10, like x raised up to the negative 10 is exactly the same as 1 over x to the 10. So these two expressions are equivalent. They're exactly the same thing. So taking the derivative of the thing on the left is exactly the same thing as taking the derivative of the thing on the right. Why do we need to rewrite this? Because this power rule up here, it only works if you're looking at x raised up to an exponent. It does not work if x is in a denominator. So this we could not think about with a power rule, but this we can think about with a power rule. So we'll go ahead and do that. Same process as before. The exponent migrates out in front. Then the new exponent is 1 less than the previous one. So think to yourself, my previous one was negative 10, but I have to subtract 1 from it, so then my new exponent is negative 11. Anytime you have negative exponents, it's always worth slowing yourself down and just making sure that you actually subtracted 1. It's really easy to accidentally get negative 9 as the exponent if you're not really thinking about what's going on. And then there's other types of algebraic tricks that we can do with this. So if I ask you what's the derivative of like the square root of x, well, we can first of all rewrite this. There's algebraic properties that say the square root of x is really can be thought of as x to the 1/2. Okay, so then now that we've used some algebra to rewrite that, this now looks like it's in a format where the power rule would apply, and indeed it does apply. The exponent migrates out in front, then we multiply 2x raised up to some new exponent. The new exponent is going to be 1 less than the previous exponent, so my previous exponent was 1/2, and I subtracted 1 to get that new exponent. Okay, so these two algebraic tricks that we just highlighted here, so let's see, going from here to here, and then going from here to here, these really are the most common like algebra techniques that you're going to have to use in the process of using the power rule. Next, we're going to look at a couple of rules that are really going to allow us to pretty broadly apply that power rule. First of all, we talk about the derivative of a constant. So the rule just says, we'll state the rule first and then we can prove it, but if your function is just a constant, then the derivative is going to be 0. So for instance, if f is equal to 3, f prime is 0. If y is equal to negative 16, y prime is equal to 0. Now, why is that always true? I'm not planning to prove most of the rules that we go through, but this one's quite easy to prove. So if you think back to that limit definition, we start with the difference quotient, f of x plus h minus f of x all over h. And what happens is when you think about, well, what is f of x plus h? If your function was just a constant, if you're new to seeing proofs, then maybe it's helpful to like think about the constant as being like an actual number, like just the number 7. If you try to plug in x plus h to this function, there's nowhere to plug it in, so all we would be left with is just the number. So we have 7 minus 7 over h. Now, I'm writing 7. Technically, like, the proof would just replace 7 with c. It doesn't matter what your constant is, but if it helps, like, kind of make the point, if you ever have a number and subtract it from itself, you would just get 0. So then 0 divided by h is our difference quotient. Well, what is 0 divided by h? 0 divided by anything is always 0. Now, the next step of the process is what is the limit as h approaches 0. Now, the entire difference quotient, which is normally the thing that we write right here, has all simplified to just be 0. So this is asking, what is the limit of 0 as h approaches 0? And the answer is 0. Now, there are a couple details, like if you really care about proofs, like there's a couple technicalities that are worth talking about, but again, in a brief calculus class, I'm just going to kind of skim over the proof. If you are interested in a more detailed proof, you can look at the book again. All right, so let's talk next about a coefficient rule. So the previous rule did not allow us to have coefficients, but we can very easily expand the previous rule by talking about, like, how do we deal with them. This is what the rule says. If you have a function, and your function needs to be some coefficient times a function that has its own derivative that we know a derivative of. So in our minds, what we're thinking of is we're thinking, okay, like I have a constant like 5, and it's going to be multiplied to x to the 6. Why did we pick x to the 6? Because it's a function I know the derivative of. Then the derivative of this entire thing, the derivative of this entire thing, is actually going to be equal to the coefficient times the derivative of the original function. So all this rule says is that if you have a coefficient and you want to take the derivative of the function, you are allowed to take the derivative of the rest of the function, and the coefficient will just hang out in front. All right, let's look at this in an example, just to make sure that it's clear what we're saying. The derivative of 5 times x to the 6 would be equal to, now technically the rule says the 5 just stays out in front, then you multiply by the derivative of x to the 6, so that's 6x to the 5, and then afterwards you would simplify. So then you would get 30x to the 5th. Now in practicality, I don't expect students to really write this down. You would look at this and say, okay, the 6 is going to migrate out in front and can multiply to the 5 to get 30, and then we'll reduce the 6 by 1 to get our new exponent. Looking at another problem, just another example, what is the derivative of like negative 7x to the 4? Well, our final answer is going to be negative 28x to the 3, because the negative 7 stays out in front, the 4 comes down, and then you subtract 1 from the exponent. At the end, you multiply negative 7 times 4. So again, don't feel like you have to show this middle step. Once you become proficient with these problems, then it's really normal to just go straight from the original problem to this final problem. Okay, let's change up our notation. What if g of x is equal to, let's call it 6 over x to the 4? Then if we wanted to compute the derivative, g prime would be equal to, well, we would, first of all, in order to take this derivative, we would have to think clearly about the original function. So the original function was 6 over x to the 4th, and we would need to rewrite this. So the original function was actually 6 times x raised up to some new exponent, and following using that same property that we used on the previous page, if your variable is in a denominator, you can just write it in line with the rest of the problem by changing its previous exponent to a negative version of that same exponent. Okay, so we're thinking about this function when we're actually taking the derivative. We apply the power rule to this function. So we would take the negative 4 times the 6 to give us negative 24, and then we reduce the exponent by 1. So for the first couple of examples, I like to just write it out because I think that helps to emphasize why we get negative 5 instead of getting negative 3, because we had a negative number and we're subtracting 1 from it. So I'm just realizing that this says proof, and it really should not. I just really jumped straight into the examples. We can do maybe one more example here. Let's look at one that has a square root. Let's say if y is equal to... Actually, let's go ahead and make it a cubed root, the cubed root of x, and then let's put a coefficient out in front of it. How about just the number 6? So y is equal to 6 times the cubed root of x. Y prime would be equal to something. That's the question. So in order to compute the derivative, what we would want to do is we would want to first of all rewrite the original function. So then y would be equal to 6x to the 1/3. Okay, so then we can apply the power rule. If you're not super comfortable with fractions, we can write it out in a little bit more detail. The coefficient just stays out in front. The exponent migrates down. It's going to eventually be multiplied to the coefficient. And then the new exponent on your variable, it's the previous one minus 1. So again, 1/3 subtracting 1 would be the same thing as subtracting 3/3. So then we end up getting negative 2/3 as the new exponent. Okay, we do need to multiply the 1/3 times the 6. So this will be 2x to the negative 2/3 as our final answer here. All right, so the next property we're going to talk about, the next rule we're going to talk about, really allows us to expand the type of problems that we're looking at. So far, we haven't tried to add or subtract different variables together, but this is going to allow us to do that. So if you have a function that's equal to just some function plus or minus some other function, a good example of that we're about to see is we're going to try to take a derivative of something like x to the 7th plus 6x to the 5th. What the property says is if you want to take that derivative, you are allowed to just take the derivative of the individual terms or the individual miniature functions. So in this case, I'm looking at this. I can think of that as being its own function. I could think of this as being its own function. But when we take the derivative of the combined addition of the two things, the rule says you're allowed to just do these one at a time. So doing them one at a time, the derivative of x to the 7 is 7x to the 6. Okay, we've checked that one off. Now we go on to the next piece. We're going to add on the derivative of 6x to the 5th, so then that would be 30x to the 4th. Okay, we've checked that one off, and we have our answer. So basically it says you're allowed to do the thing that you might have assumed that you could do. What if I ask what is the derivative of 0.02x squared minus 3 over x squared? Well, this is the same thing as if I had asked what is the derivative of 0.02x squared minus 3x to the negative 2. Okay, keep in mind, it was very important that I rewrote this second term because you're not allowed to, with our current rules, you're not allowed to take a derivative if x is in a denominator. So we would have to rewrite it so it looks like x is in line. It just has a negative exponent now. But once we've done that, we can just go ahead and take its derivative. So what we get is 0.04x minus, and then, well, let me be careful here. I have a negative 3. I'm going to multiply it by a negative 2, so I should write plus 6. And then I'm going to reduce the exponent by 1, so I'm going to subtract 1 from that. So plus 6x to the negative 3, because I took this exponent and I subtracted 1. And that's all there is to this. Now, I want to look at something that maybe actually feels a little bit more challenging just because we haven't talked a lot about the really basic situation yet. What is the derivative of 4x squared plus 5x minus 15? So we look at this and we start taking the derivative one piece at a time. So looking at our first term, the derivative of 4x squared, you take the 2, multiply it to the 4. That's going to give us 8. X, the exponent on the x should be 1 less than it previously was, so that's it, just 8x. When you look at the derivative of a 5x, some students kind of hesitate the very first time they see something like this because it doesn't look like it fits in the rule. The derivative of 5x is just 5, and the reasoning goes like this. So if f of x is 5x, you could think of that as being 5x to the 1. The derivative would be, well, how would we do that if we actually applied a power rule? You would take the exponent, you would bring it out in front, then you would write x raised up to a new exponent that's 1 less than it used to be. So it would be x to the 0. Well, 5 times 1 is just 5, and x to the 0 is always 1. So this is a really kind of long way to think about the problem, but what you will notice just every time you take a derivative of a constant times x, the derivative is just whatever that constant piece was. Okay, so I kind of over-explained that one. Then we continue on with our derivative. We've taken the derivative of the first piece, second piece. So you go look at the third piece. The derivative of a constant is always 0. So you could technically write plus 0, but please don't, because if you're adding on 0, it doesn't do anything. Okay, so having now introduced all of these properties, let's go and let's look at an example, like a more involved example that's going to ask some kind of like application of a derivative. So here, we want to write the equation of a tangent line. So write the equation of the tangent line to the graph of this function at a particular value. Now, what you need to remember is that when you see the instructions reference a tangent line, this is basically asking about the derivative. The derivative of a function will always give you slopes of tangent lines. And because we know this, we can just start answering the question. So I'm going to construct my answer over here. The generic form of a line would be y minus y1 equals m times x minus x1. There's a couple different generic versions. You could be thinking like y equals mx plus b as like a standard form of a line, but I really like this point slope form because it really kind of highlights what was the point that we used and what is the slope that we're using. So if we structure our answer like this, we basically just have to fill in 3 blanks, and one of them has already been given to us. They told us to focus on the x value of 2, so my x value is 2. Now from here, you basically have the task of figuring out what is y1 and what is your slope. Let's start with the y value. If you know that your x value is 2, you can always plug it into the function to get the corresponding y value. So let's write this down. If x equals 2, y is equal to 2 to the 4th minus 4 times 2 cubed minus 2. And as we solve that, we'll get 16 minus 32 minus 2, which should be negative 18. So y minus negative 18 is just going to be y plus 18. Next, we want to think about the slope. So to compute the slope, we need to think about y prime. First, let's compute it. Y prime would be equal to, I'm going to write the word slope down because now I'm like, this is what I do to compute the slope. Y prime is equal to 4x cubed minus 12x squared. Technically minus 0, but we aren't going to write that. When you're looking at this, it might be tempting to like set this equal to 0 or try to do something with it. There will be other problems later in the semester where we do that. But keep in mind, like a derivative just gives you slopes of tangent lines. And right now we are very specifically, we're not interested in like everything you might possibly want to know about this. What we're interested in is we're interested in the x value of 2. So all we're going to do is we're going to say our slope is equal to 4 times 2 cubed minus 12 times 2 squared. So we get 32 minus 48, which is negative 16, and negative 16 is our slope. Now, you don't have to do anything with this beyond this point. This is an equation of a line that is tangent to the function at the x value of 2. The really nice thing about this is it tells me what the slope is, and it also tells me what the y value is that corresponds to this. So my x value was 2, my y value was negative 18, slope is negative 16. Okay, next, let's look at the idea of a horizontal tangent. So in that previous example, we had a function, and I said you could set this equal to 0, but you really don't want to do that right now. So let's talk just a little bit about what are tangent lines, and then what are horizontal tangent lines, and what will we be able to do with those. Now, I'm going to frame our discussion in the context of the example that you see down there. So if you wanted to graph f of x, depending on how much you know about graphing, like probably everyone could look at this and tell me that the y-intercept is 2. And then it would be a little bit difficult to find x-intercepts because you'd have to set that equation equal to 0 and then factor it, and that looks kind of like a headache to me. So I'm not going to worry too much about my initial sketch. What I do know is that the function will rise to the right, it'll fall to the left. And right now, I don't know too much more about this, so I'm just going to kind of guess as to what the middle looks like. A fifth-degree polynomial could turn up to 4 times, so 1, 2, 3, 4. It might look something like this. It might also look nothing like this, but that's one guess as to what the function might look like. The only part I'm really confident about is that y-intercept, and then this in behavior, we're going up to the right, and then we're going down to the left. What is a tangent line? So if I put a point on this graph, a line that is tangent to the graph at that point is going to go through the point, and it's also going to look like it has the same slope as the graph at the point. So there's an example where we have a tangent line with a positive slope. If I picked this tangent, or this point over here, a tangent line should hit that point also and look like it has the same slope as the rest of the graph. That one has a negative slope. So my question is, how would you think about horizontal tangents? Well, looking at the graph, there are some places like this peak up here where if I drew a tangent line, it would just be a horizontal line. Or this valley down here, if I draw a tangent line, it's just horizontal. So anytime you have a peak or a valley, we have horizontal tangent lines. Now, later on in the semester, later on in this course, we will very specifically be really interested in this type of behavior, and we're going to use it to really kind of analyze functions. But right now, we're just introducing the concept, so I'm not going to say too much about it. What I will say, though, is that if you know you want a horizontal tangent line, we know what the slope of a horizontal line is. The slope of a horizontal line is 0, and then we can remind ourselves that when you think about derivatives, one interpretation of a derivative is that it computes slopes of tangent lines. So essentially, when you read that the question is asking us for a horizontal tangent, you know that your first derivative is going to have to be 0 at that point. So that's kind of the underlying background that you need to process when you look at this question and you're trying to decide what do we need to do. So the example says, find the coordinates of the points where the graph has horizontal tangents. Okay, I know that if I want to find the slope of a tangent, I need to compute the first derivative. So f prime of x is equal to, we'll use this same property we've been doing before, 15x to the fourth minus 15x squared derivative of a constant is 0. So the derivative is the slope of a tangent line. But since I know that it needs to be a horizontal tangent, I'm going to set it equal to 0. Now that we've set it equal to 0, you could go ahead and solve this using some algebra. We'll factor out a 15x squared. That leaves us with x squared minus 1. So then we get 15x squared times x plus 1 times x minus 1 is equal to 0. So we end up with x is equal to 0, -1, and +1 as the 3 different x values where we're going to get horizontal tangents. Okay, now the question asked for coordinates of points, so I'm going to list each of these as like a point, an xy coordinate pair. And if I want to figure out what the y value is, I simply plug in the x value to the original function. So keep in mind, you do have 2 separate functions right now. You have the original function, which tells you the y values. You have the derivative function, which tells you slopes. So plugging a number into the original function, we get 2 when we plug in 0. If you plug in -1, let's see, we would get -3 plus 5 plus 2, and I believe that's 4. And then if you plug +1 into the original function, you get 3 minus 5 plus 2, so then that ends up being 0. Now, this is the question that was being asked, so don't feel like you would have to sketch a graph of this, but because I've already sketched a graph, I now realize that it was a really bad sketch, and I'm going to resketch the graph just to improve my original diagram. So from the beginning, I knew that I was going to have a y-intercept of 2, but now I know a lot more about this. I also know that I go through the point -1, 4, so this point right up here, and I also know that I go through the point 1, 0. Now from here, we know that we're going to have a horizontal tangent line at each of these points. And there's really only a couple of ways that a graph could look if it has a horizontal tangent. Algebra tells me that this graph is going to fall to the left, it's going to rise to the right, so it's kind of natural based on the progression of the points to assume that the graph's going to have a maximum type. We're going to call it a local maximum over at this first point that you see, and a local minimum over at this last point you see. But here in the middle, it doesn't look like that's going to be a maximum or a minimum. So what we're going to have is we're just going to have this kind of little shelf-looking thing where locally it looks like the function has leveled off just for an instant, but then it's going to continue on decreasing. So this information about the derivative we computed really helped us understand what the graph looked like. And later on in the semester, we're really specifically going to be like taking derivatives and trying to analyze this as much as possible so that we'll be able to understand like what these graphs like really are doing. All right, hopefully I didn't make that sound too exciting because we're not there yet. Let's look at marginal revenue as the last example in this video. So what we have is we have a question saying the total dollar in revenues for a commodity is described by this function. First of all, what is the marginal revenue when 40 units are sold? Well, if you are being asked about a marginal revenue, then that's a question about the derivative. So we start by computing the derivative. The derivative of 300x is just 300 minus 0.04x after we take the derivative of the second part. So that's our marginal revenue function. But if you are specifically looking at 40, we can put 40 into the first derivative function. When we do that, we get 300 minus 0.04 times 40, and that should be equal to 298.40. Now, if this is a revenue, then probably the label on the revenue function would be like dollars. Okay, yeah, I'm seeing it right here. So your derivative function, the appropriate label would be dollars per unit. Now, the most typical interpretation of a marginal revenue is that, yes, it's a dollar amount per unit, but we oftentimes focus on the very next unit. So we started at 40. If our marginal revenue is $298.40, then that gives us an indication about what's going to happen when we produce the 41st unit. So marginal revenue is used to estimate the change in revenue caused by the sale of one additional unit. So if we go from 40 to 41, we would expect to have roughly very close to this dollar amount increase in our revenue. Okay, well, let's look at part B and see if the estimate is any good. So we want to find the actual change in revenue caused by the increase in sales from 40 to 41. Well, if you want to know the revenue when you produce 40 units, you just put 40 into the revenue function. This would be 300 times 40 minus 0.02 times 40 squared. Let's see what we get. Looks like it's $11,968. Then, if we go ahead and look at the 41st unit, same computation, but this time when we plug in 41, we see we have $12,266.38. Now, what was the change in revenue? We could subtract these two numbers, and we see that we have $298.38. Let's compare our answers from Part A and Part B. In Part A, the marginal revenue estimated that if we made one more unit, we were going to actually increase our revenue by $298.40. And then in Part B, we found that the actual increase in revenue was $298.38, which I would consider to be a very good estimate. All right, that finishes up this video. Hopefully that's helpful as you're thinking through these topics.